For this second session, we're going to be talking about the use of digital multimeters, or more simply, multimeters. Multimeters are a basic tool of people working on electricity. It is very important to safety to know how to use a multimeter well. We need to use the knowledge that we just gained in the previous session of the terms and parameters, current, volts, resistance, in order to know what we're measuring and how to measure things using our multimeter. Multimeters are also very important to the troubleshooting of electrical systems. So, a multimeter has four main functions. You've probably seen them, but we have a photo of one here. The primary reason for using a multimeter is going to be to measure the voltage across system components. Secondly, you're going to use a multimeter to measure your electrical current. To a lesser extent, you're going to use it to measure resistance. And a nice feature of a multimeter for troubleshooting or verify a correct implementation is you can check the connectivity to make sure that two wires are indeed actually connected. And you can do that using a multimeter. So if we were going to measure the voltage of a system, we need to know how to do that with a multimeter. So how is voltage, or what is voltage similar to in water? It's pressure. How is pressure measured in piped water systems? Well, there's really two ways we could do that if we wanted to know the pressure across a filter element. We could have a setup similar to what we see here on the bottom left, where we have one standard pressure gauge and a second pressure gauge before and after the filter element. Or we could use a differential pressure gauge, where it's one pressure gauge that's comparing the pressure on both sides of the filter. Now, I want to take a second and point out that really these pressure gauges are also differential pressure gauges. It's comparing the pressure inside the pipe with the pressure of the atmosphere. And same thing here. The only difference is that with this arrangement, we then have to manually do the math of comparing this pressure to this pressure, and the subtraction of that is going to be your differential. This does the math for us. Now, looking at this pressure gauge, now this is important because the configuration of this pressure gauge is exactly how we want to be using a multimeter to measure voltage. So, is this pressure gauge in series or parallel with this filter element? It's in parallel, because if we have a water molecule, it comes to here, it has a branch choice. We have two branches. We could go this way, or we could go this way, okay? Now, another thing to think about is how much water is flowing through this pressure gauge. None, right? We really don't want any water flowing through this pressure gauge, because if we were to install a parallel pipe like this, but we allowed water to flow through it, if you had 20% of your water flowing through that pipe, the pressure is going to be different. You can't even read that anymore. So the pressure gauge has very high resistance to flow, okay? And that's going to be important to think about a little bit later on. Now let's keep holding on to those thoughts and talk about current. What is current similar to in water? That's flow rate, gallons per minute, right? So in piped water systems, how do we measure the flow? Well, we use a flow meter. And how do we connect this flow meter to this pipe that we're wanting to measure the water in? Is this flow meter in series or parallel with the flow in this water? Well, all the flow is going through it. There's no branching. So this flow meter is in series with the flow inside of this pipe. Also, how much of the water is flowing through this flow meter right here? All of it, right? It doesn't make sense to install a flow meter that only measures some unknown amount of the water. That's not beneficial to it. So all of the flow of the system goes through the flow meter. How much resistance to flow does this flow meter have? Not much. It has almost no resistance to flow, right? Because if we had a large amount of resistance to flow in a series arrangement, we're going to change the flow rate. We're going to reduce the flow rate if this has a lot of flow, and then what we're measuring is no longer real. So when we're thinking about how are we going to connect a multimeter in order to measure voltage, you want to think, what is voltage similar to in water? It's like measuring pressure. How do you measure pressure? You measure pressure using a pressure gauge that is in parallel with the thing that you're wanting to see. And another thing to think about is that you're always measuring pressure differential, right? Same thing with voltage. You're always measuring a voltage differential. In the case of those single pressure gauges here, it's still a pressure differential, it's just we're calling the air zero. We're calling the air zero. And here, our differential, we're calling this inlet zero. So we're saying, well, if we say this is zero, how much pressure do we gain over here? We want to do the same thing with voltage. So, how do we measure voltage using a multimeter? We have a multimeter here, and we have a battery that's generating the voltage that's driving the current. We have a load, in this case it's a light bulb, and we have electrons that are flowing through the wire, through the light bulb, giving off some energy, flowing back to the battery, getting re-energized and going around like this. So, if we are going to measure the voltage, how is pressure measured in water? It's measured in parallel. We are going to take our multimeter and connect these test leads to either side of the element that we want to know the pressure differential across and connect it in parallel. If we want to measure the current of a system, we think current, it's similar to flow rate in water. How is flow rate measured in water? It's by installing a flow meter in series with the flow, because we have to have all of the flow of water go through our flow meter. Well, it's the same thing with a multimeter. We need to have all of our flow go through our multimeter. We can't measure the current if we only see a little bit of it. So we hook up the multimeter in series with what we're wanting to measure. Oftentimes that's going to mean removing a wire or cutting a wire so that we can force all of the electrons to flow through our multimeter. Take a look at where this red lead, this red wire, is connected on the multimeter right here. It's connected to the A. Also, look at this dial on this multimeter. Where is it pointing to? It's pointing to DC, direct current amps. Now let's flip back a slide and look at how we're measuring voltage. You'll note that this red lead is now plugged in a different location. It's gone from the A, amps, over to the volt side, the V. Also, this dial has been turned from DCA to DCV, direct current volts. This is very important, and you could end up burning out your multimeter if you do this incorrectly. You say, why is that? Well, remember what we said about the resistance to flow of a pressure gauge versus a flow meter, pressure gauges have very high resistance to flow. Flow meters have very low resistance to flow. So in order to let one tool, one multimeter, measure both of those variables, we have to have different modes for it to work in. So you have to physically unplug this red lead and move it over to the amp side in order to measure amps. You also need to tell the multimeter that that's what you're doing by changing the dial here. Now, let's talk briefly about measuring resistance. Measuring resistance, you have to back that up a couple seconds. All right, let's talk about resistance. What is resistance similar to in water? Your head loss, your C factor of a pipe. How is that stuff determined of a pipe? It's not measured in the field. It's measured in a laboratory where they take that pipe all by itself off into a lab, pour some water through it and measure the results of how much water comes out of there. And then they have to do some calculations on that. Well, electricity is similar to that as well. If you want to measure the resistance of an item, you have to electrically de-energize it and isolate it from the system. And then you're going to hook it up to either end of the system, just like this, so that the multimeter is just measuring, well, how well does current flow through this? You'll note you have to turn your dial to the ohm position, the omega symbol, and that wire lead is going to be plugged into the same location as for volts. And it's going to pass some electricity, just like you pour water through a pipe to figure out its roughness factor, its resistance, and then it's measuring, well, how much electricity actually flowed through this item. Now again, the most important thing is to have a good understanding of what volts, amps, and ohms are. So I love this photo. It takes 1 volt to push 1 amp through 1 ohm. 1 ohm is fighting the flow of amps. Volts are pushing it, and the amps are really at the mercy of the volts and the ohms, okay? Now, we want to take some time and practice with multimeters. So if you're with me in person, we're going to have some circuit boards in front of you, and we're going to test some different things. But I want to talk about this image here briefly. So we've already spoken about what this symbol is. That is a battery. It doesn't matter how many lines you have, but anytime you have a narrow bar followed by a wide bar, narrow bar, wide bar, that is going to be a battery. We've also spoken about these zigzags. These zigzags are resistors. That could be a load, that could be a light bulb, that could be a pump, could be a heater. It doesn't matter. We're going to call them resistors. Also, you'll see stuff that looks like this. Kind of looks like a doorway if you've ever looked at architectural floor plans. And again, we have a little doorway here. These are called switches. Just like a light switch, all you're doing is physically breaking or connecting the path that the electricity is trying to follow. So if this wire, imagine if this is a wire and it's just pointed up in the air and there's no connection to this next wire, no electricity can flow. Same thing here. If this switch is what's called in the open position, that means no electricity can actually flow through here because the electricity is going to come over here and it's just going to sit there. But if you were to close that switch so that it bridges that gap, then electricity can flow through, okay? But it's not going to flow if this switch is open. So if both of these switches are closed, then our path of electricity is going to come out of our battery. Some is going to go this way, Some is going to go this way. And then it's going to remerge on the back side here and going to keep flowing like that. Now let's say this switch is open now. That now means that current can no longer flow that direction. The only path the electricity has is going to be through this first branch right here, because we have two parallel branches, or two parallel strings, we could say. So electricity, if that's closed, can only go this way. Now let's say that that this switch has been closed, and we now open this switch. What happens? Do we get a flow of electricity through this branch? No, we don't. Why not? Well, the electricity is coming out of here, it's hitting this switch, and it's open. It can't get through there, okay? And in case you're thinking going back this other way, you don't get a full path. You could come down here, but it's not going to come back here because it's going back to the same pressure. Just like water sitting in a cup without any head differential, it's not going to be flowing around in there. It needs a complete path back to the battery. All right. So we have circuits that look just like this, and we are going to take a break from the PowerPoint and measure the volts and the current through different components of this circuit. For watching online, we will have a video of that we will share with you. If you have any questions, as always, please reach out to the engineering team. Here in Charleston, we love to work with our teams that are actually out in the field, doing the real work, doing the hard work, loving on these communities. So thank you guys.